Electricity. Everybody knows something about it. Some of us might even be experts. But for the majority of us, electricity is a bit of a mystery. We can't see it, but we can use it on a daily basis. We know it can be generated, and we know it can be distributed. Simply, we know it makes things work. The other thing that we all know about electricity is that it can be dangerous. Electrical accidents in the workplace can result in a wide variety of outcomes, including damage to plant, equipment, machinery and appliances. And of course, electricity can cause fires and explosions. But the most important outcome is the potential for injury and death, either as a direct or indirect result of an electric shock or an electrical fault. But to understand why electricity can be a hazard, we need to know what effects electricity can have on the human body and what hazards are likely to exist in the workplace. But first of all, we need to have a basic understanding of how electricity behaves, and in order to do this, we need to be familiar with some basic facts. First, electricity travels through materials which are called conductors, good examples being silver, copper and aluminium. Most metals are good conductors. The human body is also a good conductor. Second, electricity will not travel easily through materials we call insulators. Good examples of insulators include PVC, rubber, dry wood and glass. Appropriate insulators, which form parts of electrical installations, for all intents and purposes, stop the flow of electricity. Good conductors are said to have a low resistance to electrical flow, and good insulators have a high resistance. This resistance is measured in ohms. There are two other terms that we need to be familiar with: voltage and current. Voltage is a measure of pressure. A good analogy to help us understand this is water in a hose with the nozzle turned off. We have water pressure, but no movement. Current, as the name suggests, is a measure of the rate of flow. Again, a good analogy is a water hose with the nozzle open. Here we have water flowing in the hose, that is, we have a current. Electrical current is measured in amperes. We can calculate the current flowing in a particular circuit if we know the voltage and the total resistance. Simple. We divide the voltage by the resistance. Therefore, it follows that the higher the resistance is, the lower the current will be. And we will see how important this can be when we look at the effects of electrical current on the human body. As well as the facts we have just covered, there are three basic rules that apply to electricity that we should all know. Rule 1. Electricity will only travel in a circuit. That is, it will only travel in a continuous path from its source to the appliance or piece of equipment and back to its source via a different path. Rule 2. Electricity will always travel in the path of least resistance. And Rule 3. Electricity will always try to travel to the ground. Rule 1, which states that electricity will only travel in a circuit, seems pretty straightforward. We are all familiar with a basic circuit like this. Electricity flows from its source via the power point to the switch, to the light, and back to its source via a different path. If we turn the switch off, current will not flow and the light will not work. Clearly, regardless where the switch is in the circuit, if it is in the off position, there will be no continuous pathway and the lamp will not work. That is, we will have no current flowing. But what we will have is what is termed a live wire up to the switch, or in other words, we will have electrical pressure in the wire but nowhere for it to go. If this live wire comes into contact with another conductor, for example a person, a completed circuit could result and a current would then flow. The rule that electricity will always travel in the path of least resistance explains why electricity can be safely distributed. A circuit that is properly insulated literally contains the electricity within the intended conductors. It simply does not have the opportunity to escape and travel on a different path. But this leads us to ask the question, why would electricity leave a good conductor, such as aluminium or copper, and travel through a person? And the answer is that this will only happen when the following two conditions apply. First, the person must, as the rule says, offer the electricity a path of less resistance than it has in its existing path. And second, the person must also form a part of a completed circuit. This, of course, ties in with the first rule that we looked at. The resistance offered by the existing circuit could be quite high, and it is not just the resistance at the point of contact, but rather the total resistance offered by all the components that are part of the existing circuit. Obviously, this would include the resistance offered by any equipment or appliance that forms part of the circuit. This total resistance could quite easily be greater than the resistance offered by the human body. For a person to form part of a circuit, the electricity must be travelling through the person as part of a pathway to return to its source. So the person must be in contact with two conductors, one where the current enters the person and one where the current leaves the person. In most electrical accidents, this second conductor is the ground, and this can be either directly, like this, or alternatively through contact with another conductor, which itself is in contact with the ground, like this. This, of course, is where our third rule, that electricity will always try and travel to the ground, comes into play. But how does this work? What happens when the electricity reaches the ground? And how can we still have an electrical circuit? Well, the answer is quite simple. The Earth itself is a conductor, and in theory, the electricity will use the ground as a pathway for the electricity to travel back to its source. In reality, it is a little more complicated, and the electricity is likely to return, for example, to a nearby transformer. So even though this may be difficult to understand, should an electric current reach the ground, we will always have a completed circuit, and electricity will keep flowing until the circuit is broken before it reaches the ground. An understanding of these three rules, electricity will only travel in a circuit, electricity will always travel in the path of least resistance, and electricity will always try to travel to the ground, gives us a basic understanding of how electricity behaves. But if we come into contact with a live electrical source, what are the likely effects it will have on us? Will we actually receive a shock? And if so, what will its effect be? The problem the human body faces is that under many conditions, it often has a relatively low level of resistance to electricity, and a relatively small current can have a dramatic effect on the body. Typically, electricity is supplied to many industrial sites at voltage levels in the order of 11,000 volts. At this point, it is distributed through transformers to different circuits, often at different voltage levels. In many industrial sites, we will have circuits with voltage levels of 110, 120 volts, 220, 240 volts, 415, 440 volts and higher. And at the level of 240 volts, the potential for danger is very real. For example, let's assume a situation where a person has a total resistance to electricity of 2000 ohms and touches a live part of a 240 volt circuit. The current the person would be exposed to is calculated by dividing the voltage by the resistance. In this case, that would be 240 divided by 2000, which equals 0.12 amperes, or in other words, 120 milliamps, 1 milliampere being 1/1000th of an amp. If we took the same example of a person with 2000 ohms of resistance but had a 415 volt circuit, the current would be 207.5 milliamps. Both of these current levels could be fatal. The human body can detect currents at levels as low as 1 milliampere. Currents between 2 milliamps and 10 milliamps cause only minor shocks, but can lead to serious injuries. For example, a person working at height could receive a minor shock that could result in a fall. At levels of around 10 milliamps, a person exposed to an alternating current can lose control of muscles and be unable to let go of a live object. Currents in the range of 25 to 75 milliamps can be very painful, lead to collapse and even death. Currents of 75 to 300 milliamps that last for as little as a quarter of a second are almost all immediately fatal. Currents at these levels cause ventricular fibrillation, which means the heart is twitching rather than beating as normal. High-level currents tend to clamp the heart and cause burns to the skin and internal organs. So what does all this mean? It means that voltage levels as low as 30 to 50 volts can represent real hazards to people in situations where the person's resistance to electricity is low. Almost all the resistance offered by the human body exists in the skin, and hence it is easy to understand why the resistance can vary, and vary quite substantially. Thick, calloused skin, like the skin on the soles of the feet or the palms of the hand, will offer much more resistance than areas where the skin is thinner. For example, the skin on the inner forearm. Dry skin has a higher resistance than wet or sweaty skin. Broken or abraded skin has a very low resistance. The resistance offered by the human body can vary from levels as low as 500 ohms up to many thousands of ohms. Clearly, we cannot assume that we will have a high resistance if we come into contact with a live electrical source, but this large range of resistance does help explain to us why an electrical shock may be minor to one person but lethal to another. If we go back to our example of a 240 volt circuit with a resistance of 2000 ohms, we had a current of 120 milliamps. If the resistance was 30,000 ohms instead of 2000 ohms, we would have a current of only 8 milliamps, a level that would only result in a minor shock. The final point that we should consider is that the resistance offered by a person is not just the resistance of the skin and body, but also any clothing or insulating material that would be in the path of the electric current. Insulated gloves, insulated footwear such as rubber-soled boots, and insulated material such as rubber mats that a person may be standing on can, in many cases, offer enough resistance to prevent the flow of an electric current through the body. So, now that we know some basic facts about electricity and what effects it can have on the body, let's look at some common hazards that exist in the workplace. The most common cause of fatal electric shocks in the workplace is from contact with high voltage overhead power lines. Typically, these lines are not covered with insulating material. They are bare, live conductors. Cranes, tip trucks, scaffolding, cherry pickers, pipes and metal ladders are some common examples of equipment involved in electrical accidents involving overhead power lines. Many fatalities resulting from these accidents occur after the initial contact has been made. For example, in this situation, contact has been made with a high voltage overhead power line, but the truck is insulated from the ground by its thick rubber tyres. When the driver leaves the cab to investigate the problem, he touches the ground whilst still having contact with the truck and is immediately electrocuted. He has provided the live chassis of the truck with a pathway for the electricity to travel to the ground. Overhead power lines are not the only place we will find bare live conductors in the workplace. Bare conductors can also be found in enclosures containing high voltage equipment and inside pieces of equipment and machinery, typically a potential hazard during repairs and maintenance. Insulation faults, that is, insulation that is damaged or has deteriorated, can occur for a very large variety of reasons and can lead to the insulating material being either ineffective or totally removed from parts of wires, cables and cords. Ultraviolet rays from the sun, hot and cold temperatures, humidity and water can all have effects on insulating materials. Rats, other rodents and insects are known to chew into certain types of insulating materials, and obviously certain chemicals can destroy or damage insulating materials. But the most common cause of damage to insulating materials that we find in the workplace is of a mechanical nature, and this damage is particularly common with the use of extension cords. Extension cords can be dragged along the ground, dragged over sharp edges, wedged between two objects, walked on, driven over, and crushed. Sometimes extension cords are even used as ropes to raise and lower objects. All these activities can obviously lead to damage. Digging or trenching in the vicinity of underground power cables, particularly high voltage power lines, is another hazard that has resulted in many fatalities. Broken switches or plugs and damaged housings on pieces of equipment or appliances is another obvious hazard. Liquids are generally good conductors of electricity, and extreme care should be taken whenever electricity is used near any liquids. Any damp location should be avoided. Puddles, rain and even high humidity will greatly increase the likelihood of electric shock. Electrical fires can start when circuits are overloaded. If too much current passes through wires that have not enough capacity, enough heat can be generated to burn the insulating material and potentially spread to other nearby combustible materials. Sparks from short circuits can also ignite flammable materials. And electrical fires can also occur when heat is generated from pieces of equipment or appliances, either due to a malfunction or more commonly by simply having combustible material too close to a heat-generating appliance. Electrical explosions most commonly occur as a result of sparks and electrical arcs. As well as being caused by short circuits, sparks can be generated by the normal operation of some electrical devices. For example, switches, solenoids and electric motors can all produce sparks. Portable electric power tools used in areas where flammable mixtures may be present can act as ignition sources for explosions. Also, static electricity should not be ignored as a potential ignition source. In some industries, static electricity is a serious safety concern. Well, what we have just looked at are some examples of the common electrical hazards in the workplace. And the question that needs to be asked is, how should we control these and other electrical hazards? And the answer is quite interesting. Most electrical accidents occur as a result of existing control measures being either ignored or violated. Human error is the #1 cause of electrical accidents. Consider the number of standards, codes, regulations and laws that relate to the installation and use of electrical circuits and equipment. Because of its potential to cause injury and damage, the supply and use of electricity at the workplace is relatively safe because many control measures are mandatory rather than optional. The weak link in electrical safety often occurs when safe work practices and procedures are either inappropriate, misunderstood, ignored, or shortcuts are taken. Following are a number of do's and don'ts that, if followed, will greatly decrease the chances of electrical accidents occurring. Always obey warning signs. Thoroughly inspect portable power tools before use. Thoroughly inspect extension cords before use. Never use extension cords as permanent sources of power. Extension cords should only be used for temporary work. Never use any equipment which is damaged. Tag it with a danger tag and make sure it is repaired or replaced. Never use portable electrical equipment in damp locations. Immediately report any equipment which is sparking, overheating or malfunctioning. Always ensure that any electrical work is carried out only by qualified personnel. Always lock out equipment properly before any maintenance or repair work is commenced. Don't use metal ladders or metal tape measures in locations where electrical hazards may exist. Never tamper with equipment interlocks. Always have the proper authority identify and mark the location of any underground power cables before digging or trenching. And, of course, always follow safe work practices and procedures. As well as following these basic points, there are 2 other steps we can take to help improve our safety when working with or near electricity, using portable earth leakage circuit breakers and utilising appropriate personal protective equipment. Earth leakage circuit breakers are designed to detect small earth current leaks and switch off the power supply automatically. Earth leakage circuit breakers can be used in conjunction with extension cords and when using portable electrical tools. Their use will greatly decrease the likelihood of fatal electric shocks. It is interesting to note that fuses and standard circuit breakers will not provide this same level of protection. They are usually designed to operate at current levels of several amps and will function when circuits are overloaded. Fuses and standard circuit breakers are designed to protect equipment and appliances, not people. Using appropriate personal protective equipment is a must whenever we are working in any situation where we might be exposed to an electrical hazard. When selecting personal protective equipment, always remember to be sure it will match the potential hazard. The resistance offered by different gloves and footwear can vary quite substantially. Also, when considering personal protective equipment, as well as deciding whether or not insulated mats are appropriate or other items should be worn, such as insulated hard hats, consider covering nearby grounded items or pieces of equipment with suitable insulated material. This can offer further protection by removing potential pathways for electricity to travel to the ground. Electricity is a convenient, cost-effective and surprisingly safe source of energy in every workplace. Don't become complacent about the hazards associated with electricity, and remember that even though there are relatively few electrical accidents, many of these accidents have serious or devastating results.